All right, thank you. So the team, two Anthonys and a Matt, with me, we went to visit Hopkinton High. Tim took us around to a variety of parts of it. It's a quick investigation, and so there are some things that that we only kind of discovered looking on the plans later. So that you'll see a place where there's like one more piece of investigation to be done to decide what the actual method will be. The other thing that we deliberately took out of our accounting was your photovoltaic production. So we know that you have PV already. You've added PV recently that we didn't have like a full year of production on it. We don't even know what the rest of your plans are. PV is something you guys are really strong with. So our system description assumes that you have no PV. So when we say that there's cost savings, it assumes that you actually have to pay for every kilowatt hour that you consume. But in reality, most of those kilowatt hours you are producing on your building. So just kind of like take that's the particular grain of salt to be applying to our final analysis. So I'm going to first spotlight us, and I'm going to share my screen, and I'm going to let the team take over. All right. So here's Anthony and Matt, and there you go.
All right, I'm Anthony, and so the town of Hopkinton has already made great strides in their effort in reducing carbon emissions. So the systems that we'll propose today will be the next step in achieving Hopkinton's goals. We believe that after touring the school, going through the construction documents and analyzing what the goals for the town are, that our proposal is the best and most effective way to reduce carbon emissions and achieve these goals.
I'm Matt, and so there are 6 goals that you hope to achieve, which include getting information to improve capital planning, having a more comprehensive plan for high school retrofits, saving energy and money, getting off of fossil fuels and switching to electrification, adding cooling throughout the entire school, which I know that was one of your major issues, and then finally supporting the town's environmental goals, which is ultimately decarbonization.
So we analyzed all of the options to meet the town's goals, and we found the best one was a ground source heat pump. And to use a ground source heat pump, you have to install a chiller and a borehole field. We have investigated and have suggested location for the borehole fields. A goal is to add cooling to classrooms, and a ground source heat pump is an extremely efficient way to do that if coils or ERVs are installed. With added cooling, pipe insulation will be required to prevent condensation. In order to use a ground source heat pump, water temperature needs to be lowered by adding coils or ERVs.
So if we want to achieve this more advanced system, there are some changes that need to be made to the heat emitters. So to start, the heat pumps need to be operated at a lower supply water temperature than a hydronic system with a boiler would be. And by decreasing the temperature of the source water, the coefficient of performance for the heat pump is increased. So what that means is, looking on the graph on the right here, the coefficient of performance is based on the y-axis, and it just represents the efficiency of the system. For example, coefficient of performance of 4 means the system will be operating at 400% efficiency. And on the x-axis, the entering source water temperature is the temperature of the water that is received from the ground, which is typically around 50 degrees. So when looking at the green line, for example, when the system's water is at 120 degrees, the efficiency of the system is at just below 350%, or a coefficient of performance of just below 3.5. Whereas if we are at a preferred range of 80 degrees to 105 degrees, which the proposed system will allow for, the efficiency will range from 450% to just below 600%, which is a drastic increase. And this will be achieved by increasing the surface area of heat emitters so the temperature of the supply water can be lowered, and also by decreasing the load on heat emitters. And so this slide basically just reiterates what was previously talked about. And it shows that as the coefficient of performance, which is the blue line, decreases, the water temperature or the red line increases. It is also showing that for a majority of the days, the outdoor temperature is around 35 degrees. So the water temperature will not need to rise above 100 degrees very often. In fact, 98% of heating hours will be below 100 degrees Fahrenheit and above a coefficient of performance of 4.
An energy recovery ventilator, otherwise known as an ERV, is a system that helps maintain indoor air quality while improving energy efficiency. So how an ERV works is it has two vents, one's for intake for bringing the fresh air in, and exhaust for pushing stale air out. Inside the ERV, there is a heat exchanger that allows the incoming fresh air and outgoing stale air to pass close to each other without mixing. This system captures the heat or coolness from the outgoing air and transfers it to the incoming air. By recovering heat or coolness from the outgoing air, the ERV reduces the workload on your heating and cooling systems. This results in lower energy consumption and reduced energy bills while still maintaining a comfortable indoor environment. So how these are put on or installed, and they're very easy to install. They're securely mounted right on the air handler. And once mounted, the technician will connect the ERV's ducts to the existing ductwork of the air handler unit. Very easy to install. And the air handlers listed are great candidates for adding ERVs.
So there are a few air handlers that don't have fresh air as a part of their system, so they will need bigger coils. And these bigger coils will allow for cooling if condensate management is added. And some of the places that these bigger coils will need to be added include the boys' locker room, the girls' locker room, as well as the foyers.
Most of the classrooms are heated and vented with these unit ventilators, and they do not provide a combined heating and cooling. In total, there's about 56 throughout the school and 2 different kinds. They both get fresh air through the wall, and the only difference is that one is mounted through the ceiling and connected by ductwork, while the other involves the wall, and they both need to be treated differently. So during our site visit, we assumed that there was only a hot water loop that contained heating coils, and it didn't occur to us to look for cooling coils until after analyzing this unit ventilator schedule. And you couldn't imagine that this was a system that would be designed to have both a cooling and heating coil while only utilizing heating. But Tim, if that's like something you can confirm by looking at the equipment, then the solution will be as easy as making cooling coils and the heating coils to make one giant coil. And that is a simple solution. And the following recommendation is us assuming that there is only heating coils throughout the school.
So currently a class unit ventilator provides fresh air. It tempers that air as well as providing heat. And the unit ventilator needs enough heating capacity to do both and is able to do that with hot water. And this hot water is around 160 degrees. So if we want to lower the temperature water our system uses, we have to ask the unit ventilator to just do less. And this means the one job that the unit ventilator would have would be to temper ventilation air or just become a ventilator only. And this can be achieved by delivered air temperature control.
If the unit ventilator's only job is to vent, then we need a new source to handle non-ventilation loads and to address the limitations of the existing heating coil. Fan coils can be added to the classrooms.
So the current ceiling unit ventilators are not ideal for multiple reasons. The current coil is too small for low temperature hot water. They have no cooling or condensate management, and they are reported to have problematic maintenance issues.
So the current unit ventilator provides ventilation for fresh air and heating through ducts. The proposed system that we are going to propose consists of an ERV and a fan coil unit. The ERV brings in fresh air from outside the room while also removing stale indoor air. And the fan coil unit helps with heating and or cooling the building by controlling temperature. This new system will offer more efficient ventilation and heating and cooling compared to the old unit ventilator system and improves both ventilation as well as temperature control.
So we're proposing a ground source heat pump. A ground source heat pump eliminates the need for traditional fossil fuel-based heating systems like furnaces or boilers. And instead of burning fuel to generate heat, ground source heat pumps use the stable temperature of the earth below the frost line to extract heat during the winter and transfer heat into the ground during the summer for cooling. Ground source heat pumps offer several advantages, such as I already said, it eliminates the need for traditional fossil fuel-based heating systems like furnaces or boilers. There's no unexpected spikes in electricity use. The temperature is more consistent deep in the ground. They have high energy efficiency. They have low operating costs. They have low maintenance and a long lifespan. And they're extremely environmentally sustainable. But to use a ground source heat pump, you have to install a borehole field. A borehole field is otherwise known as a ground loop. It consists of a series of vertical boreholes drilled into the ground. The borehole field serves as a heat exchanger, allowing heat transfer between the ground and a heat transfer fluid circulating within the pipes. In heating mode, the fluid absorbs heat from the relatively warmer ground and carries it to the heat pump inside the building. In cooling mode, the process is reversed, with heat from the building transferred to the cooler ground.
Assuming that we're gonna use 4-ton boreholes, you'll need about 20 boreholes, which would require roughly 61,000 square feet. And you can see on the figure on the right, we proposed 3 different locations behind the middle school that this could potentially work. And we did study the middle school, but by making the field bigger, you could also tie it into the school if that's something you guys would like to pursue in the future.
So a reversible chiller heat pump system, during the warmer months, it will function as a chiller, removing heat from the building's air. And in the colder months, it acts as a heat pump, extracting heat from the ground and transferring it indoors to provide heating. A reversible chiller heat pump system can heat and cool at the same time. And by that, I mean if one part of the building requires cooling and one requires heating, it can do that simultaneously.
So the existing boiler and chiller can still play a role. Under extreme circumstances, some extra cooling or heating may be needed. But fortunately, you already have that equipment in place with the boilers and chillers, so they can be integrated. These extreme conditions only make up a small percentage of the time, so using the chillers and boilers will allow you to spend a lot less money. Since this equipment is already in place, you do not need to purchase anything further and can just use what you already have. And this brings us to the schedule. The schedule consists of 4 different phases. The first phase will be to add a fan coil unit to classrooms and replace the ceiling unit ventilators with an ERV fan coil system. Once phase 1 is complete, you'll have chilled water everywhere and the capacity for cooling. These 2 steps are completed first because they provide a benefit early on. Phase 2 will then consist of adding an ERV to all air handling units. Next, phase 3 will be adding the borehole field and connecting it to the building. And then finally, the last phase is to replace the boilers with water source, chillers, and heat pumps. And then once all those phases are completed, the new system will be in place.
As you can see, at each stage, there's both energy savings and cost savings. If you guys adopt this plan, some of the benefits would include adding cooling throughout the entire school, reducing carbon emissions, increasing heating and cooling capacity in the gym. And we know that this was one of the biggest issues that you guys had. And we think that with the addition of installing ERVs and circulating fresh air, that you'll have plenty of capacity, which will help fix that issue. And then finally, you guys would avoid replacement of the boiler, since the boiler won't be running on as many cycles, it will last longer.
And here's some projected savings. And one thing I will mention is that, as Ben mentioned when he was introducing the project, we did not calculate the impact for photovoltaics. So the cost savings assumes paying for every kilowatt hour of energy. So when accounting for photovoltaics in the future, the annual energy cost savings will only increase.
And we're happy to take any questions or comments.
Well, I'll just start by saying that was a great presentation, guys. We appreciate all the hard work that you've put into this. Very well thought out and a ton of information. I have a few questions, but I'll let anybody else go before me if they want.
No, go ahead, Tim.
So when looking at you guys identified a couple spaces for well fields to go if we went a geothermal system. Do you have an estimated amount of wells that you think we would need to operate even just the high school?
Yeah, about 20.
Okay. My question is going to be all over the map here. So the ERV efficiencies. So when you're talking about installing those, is that an ERV per classroom? and then we're using the univents as just kind of a go-through, or is it one ERV that will control a few different classrooms?
Oh, okay, so that's worth going over in detail. So for the classrooms with unit ventilators that go through the wall, these are not problematic pieces of equipment. And it's just expensive and complicated to try to add an ERV that's gonna duct to the rooms and all that stuff. So for these simple systems, we basically made the judgment that you pay for the ventilation. You're not gonna do any heat recovery on ventilation for those classrooms. Just because we're trying to keep the upfront cost low. And remember, your energy you're operating at 500% efficient. So that heat recovery during occupied hours only, it's not huge.
Mhm.
The difference is with the ceiling unit ventilators, which you identified as being problematic, which if they don't have any condensate management, even if they do have an extra coil just sitting there, we still can't do cooling with them. It becomes the problem, like if you want to do cooling, it might be simpler just to replace them. So if you're going to replace them, then we can integrate a new system we take a residential ERV, just like for a big house, residential ERV, hide it up in the plenum. It feeds the return side of this fan coil unit, which is now a fan coil unit that's sized for cooling and for heating at the temperature hot water. Now, you're getting the savings that you want. You allow the sizing of both that heating and cooling coil to be smaller because you're not delivering to it humid hot air or frigid cold air. You're delivering to it air that's already been raised to almost room temperature-ish. So for those ones where there's a ceiling to hide everything and where there's a reason to replace the existing fan coil, there we kind of compile these as a unit for replacement. And the benefit there is you can remove the exhaust air from that classroom because it's happening through the existing unit ventilator air intake. You're splitting that intake into intake and exhaust. So that's the only, and the reason that there's only what, 20 of those? I forget what the number is. So yeah, there are 20 of those. So it's not the majority. And that means when we look at our detailed savings, you can see just dealing with the ERVs for the ceiling unit ventilators, we're not getting a giant savings, right? It's not a big part of the school's, it's 2% of your carbon is related to ventilation for those 20 classrooms.
Sure. Great. That's the questions that came off the top of my head as you guys were going through the presentation. I'm sure once you deliver this, I may have more going forward, but I'll give anybody else an opportunity to ask some questions.
Yeah, of course. And while we're waiting, I do have a question from Deanna. And Deanna, it's very simple. We used a standard carbon equivalent for the different fuels and for the electricity grid as of 2024 for Massachusetts. We basically take the data from Mass Energy Insights, which is the database maintained by DOER, and we applied it to the new quantities. So that's all.
Can you repeat the name of the website?
Oh, it's not super publicly accessible. You have to be accessible, but it's using it is the standard carbon accounting tool basically that's used by Massachusetts DOER.
Oh, okay, gotcha. Thank you.
Any other questions or thoughts, things that scare you?
So if you were to look at the phases, do we have a cost of what, like phase 1 would be on and on?
We did not do cost estimating this time. largely because it's just increasingly hard to do with any accuracy. And, you know, and so we honestly, we felt like, you know, we could give you a kind of an overall guesstimate, which would probably be better than what we would have come up with, or at least more honest than what we come up with if we do proper estimating, because I've been 100% too high and 100% too low, and have seen bids coming, you know, like it's all over the map. But based on a project that I'm doing right now and therefore have the bids in, I can say that per classroom, and we know that there are 20 of them, this ERV fan coil system is about $30,000 per classroom installed with what do you call it? Prevailing wage and all the markup. I swear to God, there's a lot of markup.
Yep.
But so that's 20 of those, right? That's a big deal. Adding fan coil units to classrooms could be really inexpensive. So basically, you're just adding capacity. You've got a supply and a return pipe that's going to a unit ventilator already. And this could be done classroom by classroom, shut off valve, cut into the pipe, add a connection and a balancing valve, right? Very, very simple. Probably $2,000 in parts, and then let's call it another $2,000 in installed. So for 36 of the classrooms, that's about, let's just round it up to $5,000 per classroom. And that gets you cooling, right? That lets you use your existing chiller to provide cooling everywhere, except we do need to inspect the pipes. Like you have mostly pipe insulation everywhere, and it's mostly vapor sealed, but there are going to be joints, there are going to be valve covers, etc., that would start to condense moisture onto them once you start running chilled water through them. So finding those particular locations and insulating them would be an important step before actually running chilled water through those pipes. And we did definitely not have time on our visit to like pick out where are those locations, but we know they exist.
Ben, we're at end of life, or what we're calling end of life for a lot of our AHUs, our chiller, and our boilers. You guys are suggesting that we should retrofit what's currently there, or
I mean,
as we're looking at end of life replacement, should we be looking at some of these suggestions in a replacement schedule?
so if you have the ability to take what appear to be perfectly functioning air handling units and replace them wholesale, then obviously the thing to do is to specify them with all the characteristics that you want. So in this case, we're talking about our big air handling units. You would specify it with an ERV included. You would specify it with a hot water coil that's rated for 105 degrees Fahrenheit, right? And you would make sure that it was specified for no more than 500 feet per minute, because you're going to be running it past a chilled water coil too. You'd also specify it with a chilled water coil, right? So you're specifying all the things that we're assuming that we could reuse. Right now you have a hot water coil and a chilled water coil. If there's an ERV, your hot water coil is large enough already to run 105 degree water, because the ERV is taking that load off of it. That also increases its total functional capacity so that we're able to provide more heating or cooling to the gym, for example. Assuming, based on what we saw, that actually it's all basically functioning fine and you're probably not going to replace them. But if you've got a different capital improvement approach and you just declare things end of life and then replace them, then yeah, the thing to do is just to specify exactly what you want.
Right.
But the reason why these ones get a chilled water coil and a hot water coil, even though you've got a bunch of other things with only one coil, at least in theory, is because you can have a separate loop. You've got a simultaneous heating and cooling loop to address days like today, where you don't want to have to change over the whole temperature of that whole loop.
Mhm.
But once you move into all cooling, you can then send chilled water through what is now your hot water loop. But, so that's the only reason why on these big air handling, the central air handling units, we would want both types of coils rather than a single coil that can do both and does hard switch over. Whereas for your unit ventilators and for your other air handling units, we're talking about a hard switch over. It does heating until you're in cooling.
And what's the risk? These units are, you know, at this point, 24 years old. So what is the risk of failure on the existing units if we just add the ERV
The
to
risk
the
is,
AHUs?
the risk would be wasting money on the ERV. Right? Because you just spent money on something that now, if you're replacing the whole thing, you would specify a new unit that has all the components all assembled by the same company, you know, so the risk is throwing good money after bad. So yeah, if you are confident that systems are actually running down, that it's not just a matter of replacing a drive or a motor, or, you know, like if it's, you've got enough components that are failing, or if you've got leaks in your coils, right? Any of those things where you've got enough components that start to fail, then you really do want to start saying, well, you know what, let's just replace the whole thing. But if basically your drives are working fine, your motors are high efficiency motors and you know, don't need replacement, coils have been under good condition. I've forgotten if is there glycol in your system?
No.
So there's no glycol, so there's a pretty good chance that the coils are not leaking. There's no corrosion likely. You know, there's a really good chance that everything is in great shape and could last another 20 years. We certainly in our visit did not have time, nor would I say that I have all of the expertise to be able to assure you, yeah, this unit ventilator will last 20 years, or not this piece of equipment. I will say that, let's just put it this way, other communities that have a different tax base would never consider replacing unit ventilator, or sorry, air handling units at this stage.
Now, a borehole field, I've never heard it referred to that's a geothermal well field.
It's a geothermal heat exchanger field.
Okay.
They're boreholes, right? Because, so currently you use well drilling equipment, right? That's what you use, is the same equipment that they use for drilling water wells for like rural people who need water, you know, like my mom's house. But they may go deeper. And then they fill them, so that's your borehole. An older form of geothermal, I mean, it's still good, but it's complicated, uses the water itself. It extracts water out of the well and it sends it back into a deposition well. And those are what people think of as geothermal wells, because they're actually water wells. Here, the difference is you're inserting a plastic pipe with a U-bend in it, and then you're circulating fluid, and it's just a heat exchanger of the ground. But it's just terminology.
Yeah, and I guess that's what I'm trying to follow. So what I've heard of that terminology is that is a closed loop system.
Exactly.
Okay.
We're suggesting a closed loop system, partly because it's one that we reliably can say would work. It is not necessarily the case that it is the very best possible system, right? So if you did a test well and you found that you had what they call competent rock, which is to say you drill down and all of a sudden you hit bedrock and it's nice and solid stuff, and it's got lots of cracks in it, and you've got an aquifer running underneath, you might find that the best kind of well is what they call a standing column well. And would allow your system, would allow you to have fewer boreholes, right, fewer wells. And so they maybe take up less space, right? And higher efficiency. It's great, but it's very unusual to find all the conditions necessary to do that kind of a well. The problem with a lot of the open loop systems has mostly been filters.
Yep.
They become a maintenance nightmare. And so people are tending to not recommend that very much anymore. So it's most likely that you would end up with a closed loop borehole field. And only after drilling a test well would we know how deep it should go. Like what's the ideal depth for this location and how many you really need, right? We've estimated 20 based on the typical production of a 500-foot well from a bunch of Massachusetts locations that we know about. But this is not specific to your location. So, the first step really would be a test well.
So phase one basically gets cooling efficiently into all our classrooms.
Yes.
And then phase two gets efficiency to the AHUs, which is, and I, excuse my ignorance, but then that's going where throughout the building?
So that is all the major, you could think of it as all the major spaces, but the key thing is by doing both of these things, so all of phase one and phase two, now the new water temperature, the new maximum water temperature for the building is 105 degrees instead of 160 degrees.
Yeah.
And that is the enabling characteristic that allows you to use a heat pump.
Now,
It-
do we need the borehole field for the heat pumps or no?
Yes.
Yeah.
If it's going to be a geothermal heat pump, it needs a borehole field to do the heat exchange with. Because you have significant summer activity, significant use of the gym throughout the year, and because we think you're probably going to connect the middle school as well. And we know that I think there's a driving school, there's significant summer use. And quite frankly, you've got a pretty well-balanced building. We looked at your chiller use, and you actually have a fair amount of chiller use during the regular school year. So all of that leads to a roughly balanced heating and cooling load over the year, which means that you can extract the same amount of heat that you deposit. So that you're not freezing your field. Like the previous group that we talked with, they've got much more heating than cooling. They would end up freezing their geothermal field in 5 years. And then you have destroyed the thing you spent all that money to build. But if you have a balanced load, then you're just trading heat and seasonally storing it, basically. So for you, that is probably not only the least operational cost choice, but also because of the IRA and direct pay, also probably the least investment cost once you get your direct pay 30% tax credit. It becomes the overall best choice. And in fact, that's the case for most Massachusetts high schools that have any significant summer activity.
And then you had mentioned, which we had talked about probably years ago, whether we can make this one plant that serves both the middle school and high school. And I know you didn't evaluate the middle school, but just off the top of your head, does that mean we're doubling our bore field, or we don't know?
We don't really know, because I literally know nothing about the middle school. I haven't even looked at their energy use, but just kind of looking at it on the map, it seems like it's, kind of similar sized and probably has higher heating load, like seems like a less efficient building overall. You could probably, but I mean, this is me just pure spitball. So I could imagine maybe you use both, two of these things. Maybe you need 40 boreholes instead of 20. The upside to sharing is there's going to be hours when the high school needs cooling and the middle school needs heating. And if you use a tri-generation chiller like this one, you're actually taking heat out of the high school, and instead of putting it in the ground, you're just putting it directly into the middle school. So at that point, you're getting, say, 700% efficiency. Because you're basically doing two things that you want to do, but with one input of electricity to do it. The other upside is if you have insufficient capacity, but you've got your big chiller and it's modular, so you can just add, let's say we decided that you needed, I'm going to say it's probably going to be 5 of these chillers lined up, right? You've got them, they're all modular. And you add the middle school, you don't need to add 5 more. You probably need to add, say, 3 more. And now you have the capacity for 95% of the hours. That's going to satisfy both schools, no problem. And if you have an hour when things get really, really terrible, you just inject additional capacity from some of your existing boilers that you keep around, and your existing chiller that you keep around, and that minimizes the investment, right? Because we're talking about just a few hours per year that you might have an extreme condition. So by linking them, you get to spend less overall.
Now, when I look at these yellow squares, is each square that 61,000 square feet?
Yeah, right?
Yeah, it's like a little more, yeah.
Yeah, so if we needed to double, like you said, we would take those top 2 squares as a for instance.
Mm-hmm. Yeah. And, and the nice thing about linking it all through the high school and then sending heated and chilled water directly to the middle school without giving the middle school its own physical plant, essentially, or without its own chiller, is keeping it all under one set of controls, right? You just have pumps sending water over to here. You therefore kind of like get to rearrange the mechanical rooms in there. You have one manifold instead of 2 manifolds. So there are some efficiencies by essentially setting up a district system that feeds over here. We did not evaluate the mechanical rooms for space. So, we don't know, for example, how many boilers could you still hold on to and still have room for these chillers in that high school? And what is the space in the middle school? And what would it be if we were getting rid of things? I don't know. We didn't go there. We didn't.
So the middle school, Tim, correct me if I'm wrong, we have 2 boilers and we just replaced them in the last couple of years?
3, yeah. So we got rid of 2 pressure vessel boilers and replaced them with 3 condensing boilers.
So that's even better. So now you've got high efficiency boilers, and you've got actually these really excellent boilers in high school, even though they're not condensing, for what they're excellent quality, right? So you have like the backup capacity. So one of the things that could happen is that if you got an ambient loop, right? This is the loop of water that's roughly 50 degrees because it's just exchanging with the ground. Let's say it was a cold day. You could actually hook it up so that the existing condensing boilers, which are the most efficient ones, especially if they're operating at low temperatures, they could, if it was really necessary, bump the temperature up. Let's say the temperature from the ground you're unable to get that temperature above, say, 40 degrees because you're just so much demand, you're sending water back so cold, right? And it was just an extreme condition. You bump up that temperature with your existing condensing boiler, which is new, it's in great shape. And because you're taking water that's cold, you're going to get like 99% efficiency because you're condensing all that you can possibly condense. And then that boiler is just raising the temperature enough that all the chillers and heat pumps that can do their job. So that's another way of linking these existing equipment, and benefiting from what you have is excellent equipment.
Ben, I have two questions. One's more of a statement / question.
Yeah.
So I think we discussed that we're looking at a new elementary school, about 172,000 square feet. We're going to do full geothermal in that one, and they're recommending about 100 wells to run that building. The high school is 200,000 square feet. So I'm doing simple math in my head here, right? Without understanding the full scope. Is 20 wells, is that a concern? How did you guys come up with 20 wells as a number?
So, we're not showing our work very much here. So what we sized the high school based on your actual, fuel use. And we did a regression against weather. And I believe our R squared was like 0.98 or something. So very, very high correlation, which means we can be confident in this linear regression. That's basically the equation that describes how the high school actually performs against outdoor temperatures. And so we sized it not based on, like, you have way too many boilers. Your boiler's capacity is giant oversized. I could open this up because we did not include this in the thing. It might take me a minute to find the actual model. But that was the this might be the the model. I'm not sure. So that was the source of it. So we're actually quite confident about the heat output required and the cooling output as well. We rest against weather, did all that stuff. We'll see if I can actually find all this. So, see this. Yeah, so this is our model right there. And what we can say is like, that is a pretty good line.
Mm-hmm.
And what it allows us to do is actually size the required heat output based on what you actually have. And then from that, we've made an assumption about the heat output of boreholes. And those are 500-foot boreholes. You may have had someone recommend to you 200-foot boreholes. Or someone has already done a test well there, I don't know, and said, actually, this is very low thermal conductivity soil and rock, and so you're just going to need a lot more boreholes. Mm-hmm. It could be any of those things, or, and I guess this is most likely, they have oversized the requirement of the elementary school. Because probably if somebody isn't really built out a full energy model and done it with care, you're using rules of thumb. I mean, when you use rules of thumb, you're basically using the experience gained by people in the 1950s when you built buildings with no insulation and energy was free. and so combine all of those things on different borehole length assumptions about the borehole capacity, which could be completely wrong, right? We just don't know until you do the test well. And we did not oversize. We got very, very precise in our sizing based on how you actually use energy. As opposed to, here's the square footage and here's what, generally speaking, let's just put it this way. The last group that we did, they had recently installed new boilers and they now have enough capacity to heat 2 buildings, including one that's actually larger than the other. And so our plan is actually to steal that and heat the other building. So that doesn't mean that whoever gave you advice was wrong, and is often just a first guess. And to the extent that overestimating costs is a good way to prevent you from being surprised, that may be the most responsible thing to do. So this is a first pass, right?
Sure.
Based on a lot of assumptions.
Can I, follow-up question, and you touched on it a little bit. Is there any building envelope concerns that we should have if we were go ERV and, ground sourced heat pumps? Because of those things that you mentioned. So this building was built in 2001, probably started construction in 98, 99. I think opened in 2001.
We found only one, I mean, you were there. We found only one possible envelope improvement that was like a cost-effective envelope improvement. Without tearing off your siding and tearing out your roofs and all these things that we're just not gonna do. And even that one was going to be expensive because we'd have had to cut away this metal scrim material to get to where the air leakage is. And it's just probably unlikely to be cost effective. So we didn't find big envelope opportunities. You've got good windows, you've got decent insulation. And we know the actual performance. That regression basically says that's what your envelope is like, plus your ventilation. That's what it is. So everything that we've sized, when you add the ERVs, about 1/3 of your energy use is for ventilation air, roughly. So the ERVs are going to take that third and in the winter cut about 75% of that off, of the third, right? And in the summer, it's more like about 50%, because of humidity and their maximum capacity for moisture recovery is about 50%. So they help. They don't really impact the envelope. In terms of, if you're thinking about envelope in terms of like moisture issues, this mainly makes things better. It makes it easier to control. To the degree you've got ERVs, it's easier to control humidity. And so you may have less of an experience of higher humidity situations. What you can think about it is, right now, your cooling coil, you put the water in at 45 degrees and it comes out at 55 degrees. And any temperature higher than that, it's not doing any dehumidification, right? And you have very highly humid air coming in right now, which means you need the whole coil just to do dehumidification. But if it's coming in half as humid, right? Because you've got the ERV working. Now you only really need half your coil to do humidification, and the other half can still do cooling because air passing over a 60-degree coil is still going to get cooled down some. And so now you get, essentially, we've made your coil bigger by putting the ERV on it. Same coil, but we've made it functionally bigger. And that means you get more control of humidity and more cooling capacity, same or reduced airflow and water flow.
So I guess my final question will be, if you could explain, because I think this is probably going to interest Mr. Bishop the most, the principal of the school. What does all this mean to him?
I mean, to some degree, you've got a school that operates really well, right? You have a few events where it would be nice to have more capacity in the gym, right? This gives you more capacity in the gym. Essentially what I described with the ERV, making your coil bigger, right? That's what you're getting there. You can pack more people in there and provide sufficient cooling and fresh air. And you even have sometimes when there's insufficient heating in the gym, now you have more coil capable of doing that. You add cooling to all the spots. And what we do know, I don't have the citation off the top of my head, is basically schools where people had cooling have higher test scores. Not that they took the test in a room with cooling, but that their high school experience was in a school with cooling. A lot higher test scores. And this was at the time controlled for social and economic status and all those things that you normally control for. So, so it has an impact. we are probably not gonna be providing more fresh air. As far as I know, Tim has things set up kind of like you're doing a good job providing the amount of ventilation that's needed. You'll have less humidity concern with the fresh air because you have the ability to dehumidify it once you're circulating chilled water. You are getting energy savings, which is cost savings. So to the degree that you pay your own energy budget, and I know in a lot of municipalities, the education side never sees the budget for their energy use, so it may not impact how you budget. But let's see.
Oh, no, we have that.
But so overall, this is a savings. Remember, this is the savings assuming no photovoltaics, and we know that you guys have a lot of photovoltaics. So probably the savings is much better because here you're paying full cost for electricity and you're getting 23K per year. So maybe with the photovoltaics, we're talking about a much larger cost. Call that, I don't know, 2 sped teachers. You know, something like that, if that's how you do your budgets, you know. Other than that, I mean, these were the benefits that we talked about. You know, for the most part, you've got a modern, well-operating school with someone who knows how to operate it. Mostly, you probably won't, except for the added cooling, you probably won't notice much of a difference, you know, except being able to claim that you are a carbon neutral school. Educationally, right, you could incorporate, if you wanted to, probably at additional cost, you could incorporate the ability to see some of these systems, right? So for instance, the manifold from the geothermal well, it's at least conceivable that that could be essentially in a visible spot outdoors. I've seen some of these kind of neat ones where they become kind of an art installation and people can go and they can see water, they can read the temperatures as it's going, they can kind of understand heat pumps. You know, if you want to set up your mechanical room such that students can go on tours, a science class could certainly teach, you know, the refrigeration cycle, could teach certain things, but like that's an extra, it's not built into the plan.
So Ben, so Tim and I propose our capital plan. We put it together during the summer and we're starting to walk it out in September. So what would be our next steps using this information plan that you have put together for us?
Yeah, I would say, so there are lots of different ways to fund things. So in terms of capital, I would first, I hate to say it, assign Tim the job of investigating whether the unit ventilators actually have 4-row cooling coils just sitting there. If that's the case, right, and it just like, why would you have a 2-pipe heating loop, but add a cooling coil for no reason? But if it's there, right, if it's there, just like according to the schedule, then we're talking about a simple linking valve that turns the one heating coil and the cooling coil into one really big coil. And if you've got a cooling coil, you probably have condensate management, right? Some sort of drip tray. And then you have to figure out, well, how do we get the condensate out? And it might be as simple as pull a hole in the wall and send a tube outside, right? Through each of these wall unit ventilators. If that's the case, then you don't need to add any fan coil units. And we're talking about, you know, hundreds of dollars, not thousands of dollars per classroom. And you've got cooling. And you've got the ability to run 105-degree water. So like, if that's the case, you know, that should be part of your capital budget because you're all of a sudden you're getting cooling to everywhere. Then, this is again on Tim, to investigate the ceiling unit ventilators. Did these ones also have cooling coils? Because this says they do. But do they really? And if they do, is there really a condensate management mechanism? If there is, Tim would be mad because then I'd be saying, yeah, keep the thing, just do a linking valve and then he's got to stand on a ladder and it's just, nobody wants that. But, but it would be cheaper and you would have cooling everywhere.
Nobody cares about my comfort, Ben.
Yeah. But if it turns out that this one does not have the cooling coil, or it doesn't have a way to deal with condensate, then speccing out these, which again, we're just talking about a residential ERV. So again, I'm doing this on a current elementary school. And we've taken out the unit ventilator, you take all the equipment out, although you might leave the distribution ducts on the inside. And we basically have two ducts, hard ducts that go directly to the air intake and turn it into a split air intake and exhaust, running it to here, and then you've got a fan coil unit. It's fairly simple to specify. Probably if you've got a contractor that you typically work with on HVAC stuff, you could get them to do some so-called shop drawings to spec it out because it is pretty simple, and then price it, and that would be a way to budget for these. If it turns out that there are not actually cooling coils in those unit ventilators, then we're talking about specifying a fan coil unit for each of the 36 classrooms, is it?
Yep.
Yeah. That would need those. But again, that gets you to cooling. So that seems like a good first step. I would probably want to find some source of funding that might not be capital budget for a borehole test, for a test well, which would help. It's the first step required in sizing the actual borehole field. And of course, that can be happening simultaneous to all of this stuff.
Yep.
The next one really is, and again, could be in your current capital plan, to look at those air handling units and decide, do I think they're going to last another 20 years or so? And if you think, yeah, they're actually in good shape, there's nothing wrong with them, I could replace a motor here and a drive there, then we're talking about the design that Anthony was talking about, which is this one's from Renew Air, and it's called Applied. It's just an applied ERV, and it connects to essentially the mixed air section of your air handling unit. It doesn't have any electrical connections, it's just duct connections. The existing fans do all the work. But you'd only do that if you're sure that you're keeping up air handling units, otherwise you specify a new air handling unit.
Yep.
Same with this. If the air handling units that don't have any fresh air, you could specify a new coil that's rated for 105 degrees. It will therefore also be a cooling coil if you provide condensate management. You may decide you don't need cooling in the locker room and the foyer, in which case you don't bother with the condensate. You also have to decide, do I want to keep this air handling? So that's a separate decision that I don't think we were capable of helping you figure out. To our eyes, things seemed like they were in great shape and didn't need replacing.
Okay.
So that could be this all in this one capital plan. Borehole fields being investigated. You could technically replace the boilers with a water source heat pump if you used some of the boilers to provide heat to the chilled water, to ambient water loop, right? So this is, right, you've got the loop, it should be coming from the ground. But if you don't have a borehole field yet, and you find like, oh no, what if we have to replace a boiler? Unfortunately, you've got huge redundancy with these boilers. But you could construct a boiler loop that would provide heated water, because you only have to heat the water to say 50 degrees, maybe up to 90 degrees, right? But you're now providing a temporary loop for your new chiller so that you avoid buying a new boiler that you don't want to have in the future. So that would be a way, like, again, if you really felt, oh boy, these boilers are not going to hold out, and I just want to be safe and all that stuff. You want to avoid paying money for boilers that you don't want. So you get the chiller and you supply it with heated water, and you actually get better efficiency overall. But ideally, you would have the borehole field ready to go to plug into.
Okay. Will you send us your slides and recording?
Yes.
Perfect. Yeah, it's too bad Kelly Brown jumped off, because now I'm gonna ask her for money.
Well, hopefully we can use this information to help you with getting it.
Yep.
Okay, yes, is there anything else?
I think that's it for now. It's, I mean, for me, it's a matter of kind of digesting it and understanding it. Tim probably understands it better than I do, or does. Not probably, does.
As
so.
you're getting into the grant application phase, you know, as you're needing consultation, Lauren and I certainly don't mind helping.
Okay, I know that Senator Markey has some grant money out there, although, you know, trying to jump through those hoops. I don't know if it's Renew America Schools or if that was the Biden one and Markey has another one, but I was hoping to be able to jump into some of this. You know, the classroom, the Univet things seem to me, especially the individual classrooms, the ceiling units obviously are more involved, but getting Evans classrooms conditioned air would be huge.
Again, if those coils are there, it's really easy, right? You're just linking them. You know, it's a little bit of plumbing. It's not hard, and adding insulation, pipe insulation to prevent condensation. But yeah, then you've got it. You already have your chiller done. And I don't know if that was, I think Renew America's Schools, I could be wrong about this. I think that one was where you needed a coalition of up to, like, I think it was a minimum of 7 school buildings.
Yeah, no, I think you're right. Yeah, that's the Biden one. Yeah.
Yeah, a big process, and yeah, you know, and I think the Markey one is simpler, and it so includes focusing not just on energy efficiency, but on or renewables, but on classroom condition, you know, like indoor air quality and stuff.
Yep.
And the first step only addresses that, right? We don't get any, we get a little bit of energy savings once we start adding ERVs, right? But if we're really just linking to coils, we get no energy savings, right?
And I'm not sure if anybody mentioned it, but Mass Save should also support a lot of these things, which isn't necessarily simple, but I'd be happy to talk with you more, Susan, about the different funding options. If you want to talk those through.
If you could, because like I said, I did read up on that Renew America Schools, and you're right, that is the Biden one where you need a cohort of 10 schools together. So that's not me.
Yeah.
But Mass Save, obviously, and Markey, I'm not sure I actually have seen his yet. So, but
Yeah.
yeah.
Yeah, definitely Mass Save will support the ERVs.
Okay.
That, I know because I've got one school going right now that just got their Mass Save. This was Eversource, which one you guys are. So yeah, definitely, you can get the ERVs from them. You probably won't get the additional fan coil unit from them because they only count energy savings in the year that they provide the grant. So even though this is an investment in making the school able to operate on geothermal, which would be the energy savings, they don't count it until you plug in the geothermal heat. So they won't give you any help on getting ready, except for the ERVs.
Okay. Well, yeah, I think, you know, I don't want to hold you up. If you can send us your presentation and recording, and we can be in touch in terms of trying to find some funding, and Tim will do his homework and see if he can't get the classrooms some nice conditioned air. Evan will give Tim a raise. And, we'll take it a step at a time.
That sounds great. Yeah, we will send you all our stuff.
Okay.
All right. Well,
All
thank
right,
you.
well, thank you. Your students did a great job. Great presentation. Nice job.
Thank you, guys.
Thank you for your time.
Yeah,
Bye.
thank you. Bye-bye.